All right, guys, so let's get started. So before we study what is the response for a system, a single degree of freedom with forced vibration, okay? So this time, this is an application of what we did, which is the response to the base excitation. All right, so this time the force is not subjected to the object, but to the foundation where everything is attached. All right, so let me do a picture of the system. So this will be your mass. And this mass obviously is going to be attached to a spring and to a damper. Okay, so before this was attached to the floor, and for example, we're subjecting the mass M to a force frequency, no? To a force. So what right now what's going to happen is that what is going to be moving is the foundation. Okay, this will be the base. All right, and if you want to look at the, so here you will have y of t, and if you want the excitation of the base, okay, it could be of the form, whatever, it could be, there would be some type of harmonic function. So it would be the motion of the base, and what we'll have to calculate is what is the motion of the, what is the response of the mass. Okay, so what is an obvious application of this? The suspension system of any vehicle, no? Okay, the road has some type of variations, and this is your suspension system, the spring and the damper. What are you going to feel if you are the passenger here in the car M, no? All right. So, like always, the procedure is always the same. First thing to do is to find the equation of motion. In order to find the equation of motion, we basically have 2 to 3 steps. But for simple problem, there's only 2 steps. Step 1 is always to do the free body diagram or some type of diagram. So this is our mass M. So maybe let's start by this side now. Just by this one first. So this will be MA, which will be MX double dot. And now what would be the forces? It would be the force of the spring, the force of the damper, no? But here, be careful. Because what will be the elongation of the spring? It will be whatever this is elongating minus this one, no? Yeah, will be kx of x minus y. And this one would then be, for the spring, would be c of x dot minus y dot. All right, why do we do the figure? Is because we need to determine the equation of motion. And what is going to give us the equation of motion is the dynamic equation or kinetic equations. In this case, this mass M is only moving in translation up and down. So the motion will be given by summation of forces equal to MA on the vertical direction. So this will give us what? Minus K of X minus Y minus C of X dot minus Y dot equal to MX double dot. Okay, so if I rearrange this, we're going to have the classic equation, which would be on the left-hand side, mx double dot plus Cx dot plus Kx. All right, guys, so I just had a question, which is an excellent question, saying that what happened to the gravity? Okay, so here I'm making the assumption is that to say that the spring initially will be on stretch. Does that make sense? Because if we put mg, what's going to happen? This will have an initial compression, no? Okay, so let's say this is the position at which the weight of the mass is already included into the spring and the damper. So it has no effect. A good question. Otherwise, what will happen? You will have this equation plus a constant term, no? So the equation will not be homogeneous, and we have to do a variable substitution in order to integrate it between one of these deformations. All right. But so excellent. So here the assumption is that the mass is not affecting anything because this is already compressed on the spring and the damper. Okay. So let me write it down since you asked. So weight effect is already included in spring and damper. Let's say this will be the compressed case. All right. That was a very good question. So here now, pay attention. We have this. I remember when we studied the force frequency, we have all these terms in x, and then we have here some type of force that will be in function of t, no? Okay. So if we move now these terms, what you're going to have? You're going to have here ky plus cy. And what is y? Y will be some type of function which is sinusoidal, no? Okay. So now this becomes what? This becomes the same problem as we had before, where this will be our force excitation. F of t, no? So now this branch becomes identical as before. So now you will have this, so this will be your equation of motion. Okay, and now we need to find the solution. To equation of motion using exponential notation. Which implies what? I think that's what I finished the other class, saying that this implies that we are neglecting or ignoring the homogeneous solution. Okay, so this is important. Okay, so what is the, we're going to do it very quick, but what is the steps in order to find the solutions? We need to the solution to these equations that we need to assume a solution for x and y, no? So in this case, what we're going to assume? We're going to assume the response of x in function of the forcing frequency of y, no? Which is what we did before. And we're going to do the same thing, and let's see what we get. Hopefully, I'm not going to run out of paper. I don't think for your class, but for my next class, I probably will. All right, so in order to find the solution, we need to assume the solutions. So let's assume x of t will be equal to capital X EI omega t, where omega here will be the forcing frequency. Okay. And y of t will be capital Y EI omega t. All right, so I want to start not giving that many details anymore. So next, what is the next thing? Is we take twice the derivative of this one, once the derivative, no, and we substitute this equation. We do the same thing with the y. So substituting into equation of motion, you're gonna get on the left-hand side. So you can factor out by EI omega t. You're gonna get minus m capital omega square plus I c omega plus k equal to the capital Y k plus I c omega. Oops, I forgot sorry guys, I forgot here to put the EI. Was so concerned about the space. EI omega t. So why do we assume the same type of solution for both of them? It's because now what can we do? We can eliminate this one. And here now we can solve for the ratio of capital X divided by capital Y will be equal to what? So will be equal to this one moves here. So we have this one on top, K plus I C omega divided by, when we write this, K minus M capital omega squared plus I C omega. All right, next, just using some basic math over here. If you have a complex number, Z equal to A plus IB, this is the same thing as writing magnitude of Z, EI of phi, and the magnitude of Z, I know you know that, is equal to the square root of A squared plus B squared, no? So here we have complex numbers. So the magnitude of the ratio of X over Y will be equal to K squared plus I squared is equal to -1, so plus C omega squared square root divided by the square root, but I'm going to put that, divided by the square root of K minus M capital omega square plus C omega square. All right, so this is the magnitude. Okay, next, using the notation omega n squared equal k over m and c over m equal to 2 c omega sub n. Okay. So what do we get? We're gonna get over here. So the magnitude x over y term can be rewritten as, this is just notation. So I will do the steps here would be x, y. M omega n square factor of 1 plus 4 c square capital omega over natural frequency square root divided by m omega n square of 1 minus ratio of the frequencies, so square plus 4c square ratio of frequencies square. All right, so finally this is going to give us that is equal to x over y. So these terms here cancel. Of 1 plus 4 c square capital omega over small omega square root of hm omega n square. So I did not bring my previous class note, but what would be this hm omega? Remember, this hm omega is this term here divided by, is this term here with the omega n square, okay? Remember this one, I say this is kind of related to the transfer function, no? Okay, it's actually the reverse of the transfer function, exactly the reverse, but this is related. So basically this is kind of the magnitude, and this would be what will be giving the oscillation, no? Okay. So let's write over here, just for as a refreshment. So where hm of omega should be what? Should be just this term here. So it's 1 divided by omega n square times all this term over here, which is 1 minus omega n square plus 4 c capital omega over omega n squared. Okay, and going back, now we need to determine what would be the angle here. So we find the magnitude, what would be phi? And the phase angle, which is phi, should be equal to what? To the inverse tangent of, I'm not going to write the whole term, but this is the term over here. This is a complex number. All right. So phi should be equal to what? Is the tangent minus 1 of the b over a, no? Yeah. Okay. So b is the imaginary part and a is the real part. So instead of writing the whole equation, I'm just going to write that this should be the imaginary part of x over y divided over the real part of x over y. Okay, so let's see what would that be, what would that give you? All right, so we know that x over y is equal to what? It's equal to the k plus I c omega divided by the k minus, I'm copying from the previous page, okay? I'm copying this expression here. All right, that's the only thing I'm doing. K minus m omega squared plus I c omega. So now everything is just algebra. So in order to rewrite the complex notation, we know that, I mean, we did it before. A, right, let's multiply top and bottom by this term that will be, okay, so let's do it. Let me write it down. We're gonna have here k plus I c omega. We have done it before, times k minus m capital omega minus I c omega. So this having like a plus ab times a minus ab at the bottom. So that should be equal to what? Just a squared plus b squared. Okay, but let's write it down. So here this will give you k minus m omega squared plus I c omega times k minus m omega squared minus I c omega. So the bottom will be very simple. I mean, I don't know what we're going to have on top yet, but the bottom should be what? Should be just a square plus b squared. Okay, we already did that before on the past. We know that a plus ib times a minus ib is equal to what? A squared plus b squared, no? That's what I'm doing here to here. So on top, we're gonna have a lot more terms. So let's, so on top, we're just gonna have k of k minus m capital omega square minus I of k c omega. I'm just developing here this product plus I c omega times k minus m omega square. This will be I square minus minus plus c capital omega square. Okay, so you can see right here that this term over here will be what? Positive k I c omega squared. This will be the negative, no? It will be minus. So it looks like this one is going to cancel with kind of this one here. All right. So that at the end, what you're going to have is so the term on the denominator is not going to change because that's just already now a real value. On top, we are left with what? K minus m capital omega plus c omega minus I of the second term over here, which would be m c capital omega cube. So basically you see now that this is the real part and this is the imaginary part. All right, so that the phase angle phi is equal to what? So we have it on top is the imaginary part, which is equal to what? Minus m c capital omega cube divided by, and this will cancel, k times k minus m. So just writing this, k minus m capital omega square plus c omega square. Or using omega n squared equal k over m and C over M equal to 2 XC omega sub n. You could rewrite this as tangent minus 1 of minus 2 C ratio of natural force frequency with natural frequency cube 1 plus 4 C squared minus 1 times the ratio of the frequencies plus this times square. So guys, you see this a lot of complex algebra, no? But I think it's a good refreshment. So over here, guys, in order to save some time, because I did it before on the previous page, I did how to go in detail from this notation using the K and the C and I to use the C and the ratio of the frequencies. No, it's not that complicated, but in order to save some time, I have it on my notes. So what about I just attach this to the class notes? Would that be okay? Okay, so we'll just put it on the next page. It's just basically, we take this expression, we do the substitution, you factor it out, and just to show you how you get that expression. Okay, we're not adding anything and just take some time. So that will be 178. Right, okay, with this one there. So I'll put it on the class note that I will scan later on and upload. Okay, so let's not lose track to all this stuff, because what is the goal of all this problem is to find what is x of t, no? So we found what is the x over y, but basically y will be given to us, no, for this function. All right, so basically let's just say now. So the solution x of t is of the form that we assume. So what did we assume for x of t? We say x of t will be equal to, probably on the second page, capital X EI of omega t, no? So we need to go to the assumed solution. Okay, so now let me do this in another color. All right, so now we can find x from the expression we just found for x over y, okay, on the previous page. All right, so let's say, okay, so the expression where we're gonna have x over y was equal to what? We say was equal to 1 plus 4 damping ratio of forcing frequency over natural frequency square root h of m omega natural frequency square. Okay, so this will mean that x over here will be equal to what? Will be equal to the y times all this stuff here. 1 plus 4c squared ratio of omega n squared h of m omega. And here, let's not forget, I'm going to put it, oops, let me not forget this omega sub n squared. EI of phi. Okay, if you remember, a complex number is z equal a plus or minus, doesn't matter, a plus ib. So this is equal to what? It's equal to the magnitude z, ei, e of minus I phi, no? Yeah. So this is the magnitude, this is the magnitude. And now this is the term that we add in order to get the complex value, no? Complex equation. So let's not forget this term over here. That should be minus. I put the minus and then I forget to put it. Okay, so now we substitute this x into the top equation to get x of t, no? All right, so that we're gonna have x of t will be equal to what? Would be the capital Y 1 plus 4 c squared omega over omega n squared. Then I'm going to give you right away the solution. That way I don't have to write it twice. H capital omega n squared. And now this would be what? E of I capital omega t minus phi. Okay, again, here we use the relation that exponential of a exponential b is equal to what? Exponential a plus b, no? You see, I add this one to this one, no? Yeah, that's all I did. All right, so in that equation where phi is equal to the inverse tangent of the expression I gave you before, which is the minus 2 times c capital omega over omega n cube divided by the 1 plus 4 c squared minus 1 capital omega over omega n squared. And once again, the hm capital omega is omega n squared square root of 1 minus the ratio of the frequencies. But be careful, this one is square, everything square, plus 4 c squared omega over omega n squared. And that's it. All right, so basically you see the same process, but at the end we kind of get a different expression because this time is the base excitation, no? Okay, all right. So in this case, if we plot the same thing as we did before, oh, I'm gonna have to do something before, I guess. Okay, so in here, this is more or less the same figure as we had before. Remember, for the force frequency, second degree of freedom, what does that mean? This is, if this is equal to 1, this is the resonance, no? What happened at the resonance? We see that the amplitude goes to infinity. All right. So what is the function of the damping? Is to round off and diminish the amplitude at the resonance. Okay. But that's what we had for the force. So in this case, what happened? In this case, pay attention because we see that when the ratio of omega and omega sub n is lower than the square root of 2, which is 1.414 now, here, the response output has a higher amplitude than the base excitation input, since TD is higher than 1. So what happened is that I'm probably going to have to derive first the TD, which is the transmitted force transmitted to base. Do I really need to do that? Okay, so basically what is this saying is that this point here is critical. In this case, what's going to happen? If we look at our car, all right, we're saying when this ratio is higher than square over 2, the response x of x has a lower amplitude than the input base. So it means that this system, once you part the square root of 2, x of t will be lower than y of t. Okay. If you stay before that, what happened? You are on the area close to the resonance, no? What does that mean? That inside the car, the frequency of the ground is going to kind of couple with the frequency of the car, and you're going to be on a situation where the car is going to be moving actually more than what the ground is changing. Yeah? Okay. So if you need to design your suspension system, what do you want to be? On this side or that side? Want to be to the right, no? Okay. So that's basically the meaning of that figure over here. All right. So I'm going to put it over here with the notes. And I have another figure. Guys, also want you to notice, I mean, I don't know if it's important or not, but when I give you figures, it's not figures that I go and copy from a textbook. It's figures that I do, no? I think it's if you really want to understand the material, go ahead and try to do this figure on your own. That way you will know exactly what's happening. So similarly, now you have something for the phase angles, all right, that you see for the different dampings. This is what would happen, okay? Basically, what is that saying is that at the beginning, the phase angle will remain quite between, if you want, close to the 90, no? And as soon as you move past the ratio of square root of 2, which is the 1 point something here, no? It kind of flatten out, no? Because at that time, what you have, the response will be stable, no? Okay. All right, so this will also go to the class notes. All right, so in order to better understand the figures, now we're going to look at the force transmitted to base. So let's write over here in the case of base excitation, a force F is transmitted to the base from the spring and viscous damper. Okay, so what would be that force? And that force, you can say from here would be equal to what? Would be equal to this over here, no? These are the forces. Okay, from the figure diagram would be equal to. Okay, I will do the figure now. Kx minus y plus c x dot minus y dot. So if I do a figure here, all right, so if I do this figure here, so these figures come from here to the top. If I do it from the bottom, you should have the opposite, no? From Newton's third principle, so we have here kx minus y, and you will have cx dot minus y dot. And similarly, we have to move this force here, the acceleration, into this one. This will be pointing down, no? Yeah. Action reaction. So it will be now. Oh, sorry, it will be plus mx double dot. So this will give us this. And this should be equal to what? Minus mx double dot from the figure. Okay, I'm just doing summation of forces equals to ma, no? Yeah, okay. Okay, so that means here that you could say that f of t in function of time will be equal to minus mx double dot of t. I mean, does that make sense, guys? All right. I hope I did not stop. No, I think we are good. If we don't have the square, we are recording. Okay. Okay. And now, do we know the response x of t? Yes, we just calculated, no? Was a long expression over there. So this will be equal to what? This will be equal to, if we assume the solution, if x of t is capital X E I omega t, this will become what? Minus m. So you have the I square, capital omega square, X E I omega t. When you do the derivative, you have the I square. So first derivative will be I omega outside. Second derivative, which is this one, would be I square omega square t.
Well, it's already negative, so the negatives can stop.
Oh, sorry, that's it. I think it wasn't negative there. No, you're right. So it becomes positive. So next, what we're going to do is, this is just now notation, okay? So using here the fact that omega n squared equal k over m, which is a natural frequency. We can rewrite this as f of t over m is equal, sorry, let me do the middle step, divide by k before m. This is k. That way we do the middle step, equal m over k, capital omega squared, x e I omega t. So this becomes what? This is 1 over omega n squared, no? Yeah. So this will give you that f of t divided by the x now, capital X times k will be equal to the ratio of the frequencies, capital omega over omega n squared e I omega t. Okay. And now using the fact that we know that x, so capital X or capital Y equal to 1 plus 4 c squared capital omega over omega n squared square root of h m omega times omega n squared. Okay, we're gonna have that f of t divided by capital Y k will be equal to the ratio of the two frequencies square times 1 plus 4 c squared capital omega over omega square h m omega omega n squared e I capital omega t. Okay, so one more thing here. So if f of t for capital T is the maximum amplitude of f of t occurring at e I omega t equal to 1. So that means what? At t equals 0, no? Okay. So when that is equal to 1, you find that the relation F cap lower capital T over Y K is the same expression as above, but we just remove that expression here, will be equal to what? Capital omega over omega n squared. And if you want now, okay, here I have it in function of already of the, so it's already putting the value of the HM capital omega. Square at the bottom, I'm gonna have this expression, which is what? 1 minus ratio of capital omega, omega n square square plus 4 damping ratio omega over omega n square. And instead of writing the square root top and bottom, I'm just going to put it here outside the bracket, okay? Power to the 1/2. Okay, so now if we look at the figure of f of t over the base excitation, what can you say? I mean, what can you observe? That basically you see that the force excitation is kind of have the same behavior as the response x of t that we just analyzed here. So for example, if you have to compare this figure with this figure, do you see a big difference? There is almost no difference, no? They have the same behavior, no? Okay? So that's basically what happened, is that the force response actually acts in the same phase, so the amplitudes will be different, but it should work on the same phase. So there's no phase difference. So if you want to write it down, and I will put this figure over here. So note that the transmitted force, remember, transmitted force to the base, so F of t, is in phase with the response x of t. I mean, okay, so let's go back to the initial figure. Okay, understanding the problem. So this is what we're trying to do today. What we did today, find the response for base excitation. So in this case, the capital Y will be given. Now the capital Y on this figure will be the amplitude of the response. All right. So we found what will be the response x of t. Now, because this is moving up and down, this is going to create a force also on the base that we just calculated to be f of t. Okay. So will it make sense that this force that is induced by K and C is going to be in function of x of t, no? Yes? But what is the biggest difference is that the force created by this is going to be in phase with whatever is happening with K and the damper. Does that make sense? I mean, it makes sense, no? Okay. But realize that the opposite is not true. This is moving, but because of the damper in the spring, this might be moving. This is the floor. Okay, so it's not the force, it's not the force. No, this is the floor. This is out of phase of whatever you're going to feel in your car, because there's a time delay between when this base, when your car feels the obstacle and when it comes to your seat. No, there's a time delay, so then there is a phase angle. However, now when this is going to start moving, your suspension system is going to move. It's going to create a force on your base, no, on your tires, and that one should be in phase because it's no time delay. Okay. All right. So I'm going to put this button actually here. So we have 15 minutes, so let's start maybe a problem that we finish next time. But at least let's do the problem statement today, and we'll solve it next time. Or no, maybe we can do something. There we go. All right, so I will give you these notes, okay? If you want, you can write it, but if you want to save some time, I'm going to post them, okay? So let's do a problem. So consider an automobile traveling over a rough road at a speed v, okay? So let's say the speed is constant in kilometers per hour. The suspension system has a spring constant of K equal 40 kilonewtons and a damping of 0.1. So basically, in this problem, they give you C, but they could have give you perfectly C, no? Okay, all right. The road surface varies sinusoidally, so sine function, and you see they always give you the amplitude. I mean, not always, but they generally will give you the amplitude. So this should be 0.05 meters. That would be about 5 centimeters. No, that's not much at all. And a wavelength of 6 meters. So what does that mean? That you will have a bump every 6 meters, no? Basically, so we'll vary it this way. Okay, so it looks like I put over here, write a MATLAB code to find the displacement amplitude of the automobile for the following conditions. Mass of automobile is 600 mt, so for m equals 600, m equal 1000 loaded, and for different velocity of the automobile, which is 10, 50, and 100. All right. So I'll give you everything that I have here on the notes. So basically, first thing I do, this is, I think, the figure of the problem. You see, in this case, they give it to you a bit differently. You could have just plot one spring, no? But here they do two, whatever, no? To make it more difficult. Here, this is your tire, and they tell you this is the surface, this is the amplitude, this is one cycle, so this would be the wavelength, okay? So again, first thing to do would be to find the equation of motion, but you know exactly what the equation of motion is going to be. This what we just did, no? Yeah? Okay. Oh. All right, what we just did. Same equation. Here again on the problem, I say assume the solution, and I go very quick. And we have this expression here. So now we know the K, we know the mass. So we're going to have how many different natural frequencies? 3 different cases, no? So here looks like I do this sample calculation for m equals 600 and v equal to 10 kilometers per hour. So in that case, you have K over m. This is the natural frequency of what? Of the car, no? Yeah? All right. So I do this. So it's 8.1649 radians per second. Now I need to find what is the frequency of the road, no? Yeah. So how can we do that? So to determine the frequency of the road, we know that this is one period. So it will be over a period of 1 second. This will go during 1 second, will go 2 pi, and this will equivalent to 6 meters. Okay. So how do we go from one to the other? We know the frequency is velocity over length. Look at the units, should be 1/2 second, no? All right. So we know the velocity. we know the space between the peaks of one cycle. So this gives you 0.463 hertz. Now, to go from hertz to radians per second, what do you need to do? Multiply by 2 pi radians. All right. So we're going to get, this is now an omega, capital omega of 2.909. We probably by now, you remember this expression that we wrote many times today, no? Okay. So we have that the amplitude of the response is equal to this. So the ratio of the amplitude of x with respect to y is 1.1445. But do we know why? Yes, it was 0.05 meters, no? So we can actually find x. Yes, on the problem. What is this one? Trying to save this for you guys. So we know y over here, no? Yep. So we know y. We can find x for the different cases. So this is for the n equals 600. We need to do 3 different velocities. Yeah. N equals 1000. 3 different velocities. You find a different x. Okay. And here I give the different values. So here, notice this. I think I have it on a figure, but maybe you can do it from the data. Which one is higher? So imagine this is the, what was this velocity? Goes from 10, 50, 100. So this is 10, 50, 100. 10, 50, 100. 10, 50, 100. So what's happening as you increase the velocity? The response that you're going to feel in your car is smaller, no? So this is actually saying that if you see a bump, looks like it's better to go fast over the bump than slow, no? Okay. So, this is what the math is saying, okay? I'm not saying do that, okay? But basically, this is what this is saying over here, no? All right. Let me write this. So 77, 78, 76. Okay, so exactly what I just told you here. From the table, it's observed that the velocity of 10 kilometers per hour, the amplitude x is larger than the amplitude of the bump on the road x equal 0.05. So it's true. What was the case here? 0.0572, no? All right. So as the speed increases, the frequency also increases and the amplitude x reduces significantly. This is what I just told you. All right, so I'm going to put all this to the class notes. That way we are done with it. In order to do the calculation, this is very simple. This is a MATLAB, but basically I just write the equation for M and V, no? I mean, it's I do the for loop because it's 2 cases for this and 3 cases for the velocity, no? Okay, so I mean, I don't even think you need to do the loops anymore. I think you can put inside this bracket like 1, 2, 3 or something like that, and it would work, no? But basically, it was just for the data. Okay, this I also will add this. I don't know why I did it this way, but it looks like this is a Maple file for the sample calculations. Oh yeah, I'll probably use this because of the notation. Oh. So why didn't put here the capital omega? I have no idea. But I mean, basically for the notation, because this is omega over omega n. But it should be the capital omega. I don't know what I did, but basically I saw over here for the frequencies, for the amplitude 1.1415, and basically just to give you the response, okay? But you don't need to do that in Maple, you can do that in MATLAB. But I will put it also with the notes. Looks like I did a figure over here showing that with the velocity, how will the amplitude decrease, okay? And this would be for 2 different case over m values. So this one looks is the one for 610, no? I don't know what would that be, but basically you see that you go from a larger amplitude to a smaller amplitude as you increase the velocity.